So today we have a double session, the first part of which will be started by Chris Power. He'll be presenting the history of light sheet microscopy, where he will explain why the most common implementation is not an upright or an inverted microscope, but actually a horizontal microscope. So Chris will present variations of sample mounting techniques and discuss their relative pros and cons. And he will show sample images and cover both live cell imaging as well as imaging of cleared samples. So Chris joined Carl Zeiss in 2004 to help bring light sheet technology to the market. He's imaged a very wide range of samples and will be happy to answer any questions you might have about sample mounting. And we can ask questions directly after his seminar before Ramon starts presenting his part of the seminar. So Ramon Ramirez will present on the clarity technique after Chris Power, and his seminar will be in Spanish. So for a bit of background on Ramon, he studied at Universidad Católica in Valparaiso, where he obtained his biology degree. Then he went to Universidad de Alcalá in Spain to gain experience in scientific imaging. And then he came back to obtain his PhD at Universidad de Chile. And in 2018, he joined our Center for Integrative Biology at Universidad Mayor to manage our microscopy hub. So, and a lot of his time now is dedicated to light sheet microscopy, and he can help you get started. But for now, I'll leave it to Chris to start with his seminar to talk about an introduction to light sheet and sample mounting.
Okay, so hello everyone. So I've got the screen here and a camera here, so if I look a bit distracted, not quite optimal. Yeah, as mentioned, I started with confocal 23 years ago. And I worked through various technologies such as multiphoton, and eventually I ended up at Carl Zeiss looking at light sheet microscopy. And so I spent quite a bit of my history covering light sheet in particular. And as mentioned, because I've looked at quite a few things during the Q&A, if there's something I've not covered, please feel free to ask away. But yeah, what I'm going to cover initially is how light sheet came to be, how we started this as a machine for looking at live samples, such as the image on the left here. This was one of the first images taken from the prototypes, and how that system changed from being just a live cell system into a clearing system. I know there's some repetition with some of the course that was also given about 6 months ago, but yeah, hopefully it's still useful. The main drive behind light sheet was at the time, back 20 years ago, people were using confocal, and as popular as confocal microscopy is and variants of confocal, it was only really good for things that were maybe 50 microns, 100 microns thick. Now, I know those systems have got better at looking at deeper things, but for those of us who look at organisms or tissues which are thicker than that, the confocal just wasn't up to the task. And so we wanted a system that looked towards live samples, but live thicker samples, such as you see here. And this you also see today in this kind of paradox discussed sometimes in things like Nature, where experimentally Petri dishes and slides are really easy, but they're not so physiologically relevant. And so what you want to do is try and think about where on the spectrum you are, and light sheet definitely helps us shift right on the spectrum. Now, I said I would cover the history. I'm not going to cover all of the history, and I'll paste in the chat later on this link from Nature. Nature has a fantastic history of microscopy, but what I would point out is light sheet started really early on, and it came together from several things at the same time. So staining in microscopy was coming along. I'm not going to talk in depth about that, but eosin, 126 years ago, being the first real fluorescence label. But that was actually invented before fluorescence microscopy. So fluorescence was going on here, but fluorescence microscopy really started in 1904. And if I describe how we got from fluorescence microscopy to light sheet, I'm going to show that over the next few slides. So when people talk about microscopes, here you see a classic microscope on the left. Really, microscopes do three things. And the first everyone knows is make small things look big, but you also care about resolution and you care about contrast. Now, 130 odd years ago, people were really looking at contrast. People were inventing all kinds of different condensers and ways of shining light in at different angles in order to try and maximize contrast. Viewing the fact fluorescence didn't exist in microscopy back then. And so back in 1902, this is the first light sheet microscope. So Zsigmondy and Siedentopf came up with this design here, where you basically had an upright microscope, but you shone light from 90 degrees. And this they did not in fluorescence, but as a form of dark field illumination. And this became commercialized. I think Zeiss sold 6 of them. It was that popular back way back then. But it was an interesting enough technique that Zsigmondy went on to win the Nobel Prize in chemistry for some of the work he did on this microscope. And I just show one image from that microscope back in 1926, looking at colloids. But that, whilst interesting and Nobel Prize is great, it wasn't the main focus. It wasn't the main drive that made Lightsheet what it is today. But back on those early systems, I mentioned resolution, magnification, and contrast. They had magnification from the microscope, they had contrast from the 90 degrees, and they wanted to improve resolution. And to do that, Ernst Abbe at Zeiss had come up with the famous resolution equation, which, for those of you who aren't familiar, basically says the resolution of a microscope is determined by predominantly the wavelength of light and the NA. NA, you work on the lens design, and wavelength, you try and go shorter in the wavelengths. And so Siedentopf back then worked with Kohler. He put a UV light source into the light sheet, and they noticed that things started to glow. And that was really the foundation, 1904 to 1908, of fluorescence microscopy. Now, fluorescence microscopy went in a completely different direction. And they kind of gave up on this horizontal design for many, many years. And fluorescence microscopy became the big thing we know today. But light sheet disappeared, or so we thought. It kind of meandered into different industries. It went into looking at macro studies, so fish tanks meters in size. And then it moved into the industrial environment, where it was used to do things like looking at shipbuilding. So you build a ship. How do you know that the metal along the hull is correct? And Ridley Scott grew up on the shipyard. So many, many years later, he mentioned to James Cameron, when he made the film Aliens, this is now in like 1986, he mentioned this trivia about if you run a light sheet along a solid object, you can get a really good feel for the structure of the object. So as far as I know, this was the first mention of light sheet in a film in Aliens in 86. But all this time it had been forgotten in the world of microscopy. Now, not long after the film Aliens, in 1993, there was a guy, Dr. Voy, who actually brought light sheet back into the world of microscopy. And he did that because he was looking at guinea pig cochlea, a very large structure. And he wanted something that, basically a quick and easy way of doing sectioning on these specimens. So he called it opphos, and unfortunately, it wasn't very well adopted or seen. So whilst he did it, no other people copied him at that time. Now, separate to opphos, over at the EMBL, Ernst Stelzer was working on a concept called theta microscopy, which gets to the heart of one of the key advantages of light sheet. So we all know from confocal, you have this NA and you're looking at your cells on a cover slip. But if you want to go deeper, very often you need to have a lens which has a larger working distance, and larger working distances inherently have lower NA. And because they have lower NA, in order to get the working distance they need, it means the resolution is degraded, particularly in the Z dimension. And so what Ernst was trying to do with theta microscopy was to couple two light sources in a confocal microscope at 90 degrees. And by doing so, the point spread function, or the resolution you get, is actually the multiplication of the excitation and emission PSF. And this means that by splitting your confocal and doing it at 90 degrees, you end up with really good X, Y, and Z resolution. So this was a great idea, other than it was a complete nightmare to build. So it never became commercialized. That's not how we do confocals today. It was too hard a concept for the gains that were being looked at. Now, within that lab, 10 years later, there was a PhD published from Jan Huisken. So Jan did his PhD under Ernst Stelzer, and he ran with this idea of theta, but he changed it to using, instead of a point illumination, a line illumination, but this time in a fluorescence or a full fluorescent microscope setup. And it was coined selective or single plane illumination microscopy, or SPIM. And this PhD was really the foundation of modern light sheet. So 102 years after the first light sheet, it came back to Zeiss as in its fluorescence form. And this is when I joined Zeiss to try and commercialize this idea. So why was this idea suddenly so popular? Well, the main reason was the way in which the light is put in has a couple of really key advantages. If you think about a normal confocal, you image a zebrafish, the plane of interest is illuminated, but you also illuminate everything above and below. Whereas in light sheet, you only illuminate the key plane of interest. You don't illuminate above and below. And this means the more Z you have, the more Z sections you would need to acquire, the better the reduction in photo bleaching. So simply put, if you have a zebrafish which needs 300 Z planes to acquire, you are 300 times gentler than doing it in an LSM or some other technique. Now, and that's just because of the advantage of only illuminating the plane of focus. And you can use this sensitivity to, do you image for longer, for quicker, from multiple views, etc. That's one advantage. But the other advantage is how you get that light into the focal plane, or how you spread the light. And this is important because back 20 years ago, people cared about, do I bleach my sample or not? That was the key test in a confocal demo. This one bleaches 20%, this one bleaches 50%, 20% less, that's better. And if you didn't bleach, this was great. Nowadays, it's known that even outside of bleaching, you can still cause phototoxic, photo damage effects, particularly in live samples, even putting light in that doesn't necessarily bleach. So we want to be as gentle as possible. And just to kind of illustrate that effect, if you think about a 1,000 by 1,000 pixel image, with a confocal, you put all of your light on 1 pixel so a millionth of the pixels for a millionth of the time. So you have to be a million times brighter to get the same average intensity. And to do a kind of crude analogy, if I subject you to light, would you like a millisecond near the surface of the sun? Would you like 3 hours outside in Jamaica at noon? Or would you like a month in a basement with a candle? Now, the same number of photons is going to hit your body, but near the sun, it would kill you. Near Jamaica, you might get burnt. And in the basement, you'll be absolutely fine, even though the same amount of light hits you. And so in this analogy, confocal is like being near the surface of the sun. You get really subjected to an intense amount of light for a very short period. Spinning disk, one of the more popular techniques for imaging, is a lot less intense, but is still relatively intense. Whereas light sheet, because you subject everything to light simultaneously, and you can be that much weaker, it's like being in the basement with a candle. It's so much friendlier to get the light into the sample. So that's the main advantage, is its sensitivity. But the other advantage, I alluded to with the theta microscopy is that because in Lightsheet your PSF is determined by your excitation and your detection, then as depending on the lens you choose, you tend to always get reasonable sectioning, because if your detection lens is poor, your light sheet can be relatively thin, you get good sectioning. And if your lens is very good, then that can also bring down sectioning even with a thick sheet. Now, just to get your head around that concept, I like this graph, which isn't often shown, but is really key for light sheet. On the x-axis, you have NA, and on the y-axis, you have sectioning. Now, depending on your design and microscope, the curves might change slightly, but what this shows is the red curve is confocal. So with high NA, confocal will give you better resolution than a light sheet. But if you want a 10x or a 5x or a really huge field of view because you're looking at something big, especially the cleared things we'll get to later, then your Z resolution becomes atrocious. It becomes really, really bad. And if you're down here, confocal almost becomes useless. Whereas with light sheet, you get pretty good resolution with the high NA, but as your NA lowers and as your field of view gets bigger and bigger and bigger, you still maintain good Z resolution. And that's why light sheet has become really, really popular for looking at big things, not just live, but also cleared. Now, just to kind of carry along the evolution, back after the 2004 paper, people were doing all kinds of optical benches to try and get this system made. And we were looking at different architectures and ways that we could build this microscope. And we were looking at different designs. We eventually went for this kind of a setup where you have a detection lens at the back and you have excitation lenses from the side. So you would have your sample here, and we would present the sample by hanging it. So here we have a zebrafish in transmission, just showing this kind of, we call it an agaro sausage preparation. I'll come back to that a little more later, but dangling in front of the system. And so really the first system we built was this. This is an axiomager, which is an upright microscope. And that's how we put it. So we laid the microscope on its back in order to have the lens not looking from above, but looking from the side. And the reason we do that is because if you're looking at bigger samples, it becomes hard to get them in front of the lens because they can flop around. If you hang them and use the gravity axis, they can maintain their shape as you move them in X, Y, Z rotation. So it's a much, much better orientation for looking at big things. So it's not that light sheet has to be horizontal. It's just if you're using light sheet for big samples, horizontal is really important. Now, this microscope was great. We looked at it. We went the sectioning of a multi-photon, the speed of a signal to a spinning disk, and the signal to noise of a wide field system. It had some issues, mainly that there were some artifacts. It was hard to deal with data and so on, but we dealt with all of those in the product development over the next few years. What was really key about this microscope, and if you've never used light sheet, I really have to push this point, is you get this kind of image. Now, this is a 2D XY image over time. So just a time lapse of a single optical section. The movie I hope you see playing now is 25,000 frames, non-stop imaging of a zebrafish. So you might look and it looks like the movie's still. If I move my mouse, you can maybe see the progress bar here. Occasionally, you will see this fish twitch. Occasionally, you might see some calcium flashes. But the first image, the first day on the light sheet, we saw this kind of image. And we went for lunch and we came back. And I went and put a glass of drink on the table. Shouldn't have in the lab, but knocked the table and the image shook. And we realized we'd been imaging at 13 frames a second non-stop for about 40 or 50 minutes. So 25,000 images and the sample hadn't bleached. And that was a combination. It was mainly about this fact that you're doing parallel illumination and therefore you are so much more gentle. So that was, yeah, when we realized this is really, really powerful, especially if you're used to confocal with the noisy kind of scan as we go here. Okay, so we went through different prototypes. This was the, the next system that we looked at. And what we realized was that a lot of the home build systems, they had some issues because you either had bad optics going into chambers, or you had lenses that went into the chamber like this, but this was very hard to clean. And what we wanted was a system that was usable. So we wanted a big chamber, lots of room to get big samples in, but with good optical performance. And at the time, there weren't any lenses that would go from outside the chamber through a few millimeters of air, through a glass cover slip, through a centimeter of water, and then still be chromatically correct. Luckily, we at Zeiss know a good lens company called Zeiss. So we designed some lenses that would allow us to do this and have a big, easy to use chamber here. And that was what became the Z1, the newer model being the Lightsheet 7. And the light path, I'm not going to go through all of it, but basically we have different lasers here that we turn into a light sheet. We send into the sample via the left or the right, and then we go through the detection lens, we block the laser light, and we detect this on 1 or 2 cameras here. And the first use of this system was really stereotypically for looking at big developmental biology samples. So zebrafish, Drosophila, Arabidopsis were the 3 kind of key samples that everyone started to look at. And that was because you could get movies like this with high resolution, high dynamics, quick system, and you could also rotate your specimen to look at different angles. And because the system was very stable, you could do this for minutes or hours. So you see here, this is I'm trying to remember how many hours, but you see the hour counter in the top right here. And soon people started to use this for different developmental models. Because it was horizontal, it became quite popular for plant biologists because you could keep things aligned, and plants, either want to go up or down, depending on if you're looking at the top or the roots. So from a geotrophic perspective, Lightsheet was very popular. And yeah, here you see samples imaged for 90 odd hours. The record on the Lightsheet is about 3 weeks for some slow developmental beetles. So again, this is just showing, this is the same root imaged at 0 and 90 degrees, in this case, growing down overnight. And this is the same Arabidopsis plant, slightly higher up. Now, coming to how do you mount the samples? We want to mount by hanging the sample, because that lets us move through the Lightsheet easily. It lets us keep big things structurally sound. Now, the first method for mounting was what we call hanging. This is physical, tactile grabbing of the sample. Now, it could be a hook, it could be glue, clamping. In the early days, we were looking at malaria inside mosquitoes, and we did that by putting super glue on one of these poles, letting the mosquito land, get stuck on, and we just put it in the chamber. Now, this technique originally became less popular, but with cleared samples, this became more popular again. So this is still done probably a third of the time, I would say. And this is also probably the most flexible, because it's really the limit of your imagination on how we trap things here. The second technique is what we call embedding. So this is where you have a sample which is too fragile in order to use the hanging method. So this might be clumps of cells. It could be small organisms such as the fish or the Drosophila I showed. And here we do embedding. Now, typically this means putting the sample in agros. And if it's live, we normally use low melting point agros, which is around about 30 odd degrees, but you put it in and you try and cool it down as quickly as possible. And once it's done, you put your sample in, you suck it into a glass capillary, and then once it's set, you push it out. So you just image through the agros, not the capillary. And this kind of agros sausage will let liquid, it will let gas exchange, media exchange take place, and yet it has a refractive index very close to water, so our optical quality is good. This, at the time of the Lightsheet launch, became by far the most popular technique because it's easy. I should mention as well at the end of the chat, when you get the Lightsheet, the manual has a chapter written by one of our collaborators at the MBL who has done many, many ways of mounting here, and I will upload that PDF which covers some of these techniques. So if you're thinking, you know, how do I do X, maybe have a look at this PDF later. Now, the embedding technique was popular until people started to be a bit more ambitious, and they realized there were two flaws in this. The first flaw with embedding is that it keeps the sample restricted. So if you have, say, a fish trying to develop over time, it can't necessarily uncurl its tail, it can't spread out. The other thing was that people were more ambitious in the range of model organisms. And if you try and do, for instance, mammalian embryos, they can be very fragile and they don't like the low melting point agros. So the third technique, which was very unpopular originally, but is growing a bit in popularity, is encapsulation or enclosure. And that's where you might have something, either a bucket made of agros, or the most popular is FEP tube. So this is a polymer used in flow cytometry. And you have like a drinking straw made of this see-through plastic with a refractive index close to water. So you can suck your sample in, you can seal the end, and then you have your sample happy inside. So yeah, that's the three main techniques. As I mentioned, the main one, the most popular one is literally this. You know, here's a cuvette, low melt agros on your fish, suck it up. And the FEP tube, as I mentioned here, this is a fish below that was kept in 1.5% agros and couldn't uncurl during its development. And the top is what you would get if you use the FEP tube method. But it depends. If you're only looking at your fish for a few hours, the agros technique works fine. And once you've mounted it, you put it into the top of the chamber here, and then load it into the chamber where we can have full environmental control, temperature, and so on. So that's what it looks like. Now, in terms of the range, maybe at the Q&A or afterwards, we can talk about it. My colleague here put together a list of things that he's imaged over time, and it really is anything that you can get light a few hundred microns into, which is reasonably big. We've tried a whole range of samples. To give you an example of where we sometimes think a little bit different, this was a neuronal sample, and hang on a minute, I think we come back to that one, but yeah, this was an example with I forget the model embryo here, but this was looking at cancer cells, I believe. So again, you're not getting on an uncleared sample, you won't get all the way through, but you can look from different angles and see a few hundred microns in. And we have different ways of mounting specimens here. So we have different holders depending on how you might need to mount. Yeah, I think some of the slides are slightly out of order, but here, those brain slices I showed earlier, here you have it loaded with a calcium indicator. We use filter paper to just kind of mount this tissue. And then here we have our imaging lens, our excitation lenses, and the tissue here. Now, of course, we put the chamber in, lower it into the chamber, and then on the left, this is showing the kind of signal to noise and frame rate you can get looking at thunderstorm of calcium activity in the brain. Okay, so yeah, this was really how the Lightsheet originally came to market in 2012, and it was very popular for long-term time lapses such as those you see here. It's also worth remembering that you don't always have to do volumes. You can just look at a single plane if you want very quick dynamics. So here you see blood flow in a zebrafish heart. Here you see very quick movement inside. I think this is the skeleton, the cytoskeleton within plant. And yet really a range of organisms. The resolution isn't great for individual cell work. Here you're better with a confocal, but for bigger samples, it became very popular. And there were also a few ways of improving the image quality in these larger samples. So the first one was that if you've got really dense objects or things that cause shadowing effects or block the light, here you might get stripes within your sample. And on the light sheet we sell, you can pivot the beam. It's just a checkbox in the software. And that means that if you have something that blocks the light, you can avoid as you pivot up and down here. Now, of course, light, it still has a maximum depth of penetration in uncleared samples. Here you see a zebrafish, and I don't know if you can see the scale bar here is 100 microns. So this is about 600 microns across. And here, more so in the right image, also in the left a little bit, but here you see the light gets about 300 microns and then it begins to scatter. So this is what you would see on a confocal if you were going from above or any microscope, you get scattering. But because we've got the illumination from the left and the right, we can alternate those and take an image from the left, an image from the right, and then fuse those together. And this will let us get imaging of allow us to get good imaging of specimens which are medium size, so a few hundred microns, getting the best image from the left and the best from the right. Now there are some samples where that isn't good enough because you still get light scattering, and that's where multi-view imaging comes in. So multi-view is something you could in theory do on other techniques. It isn't Lightsheet specific, but it's mainly done on Lightsheet because Lightsheet's the only system where you really have the speed to get volumes to do this. So here we see a Drosophila imaged from 4 different angles. So take a stack, rotate 90 degrees, take another stack, etc. And here you see 2 views taken at 0 and 180 degrees. And you see that neither of these Z stacks has the full information about the Drosophila. But if we digitally rotate and stitch those samples together, we can get the full specimen here. And this multi-view fusion works well on samples which are greater than you can get in a single view, but where 2 views can fuse together nicely. So typically in that 500 micron range. So that was how the confocal came out 2012 up to about 2015. But then people began to come to us more and more and ask about cleared samples. Now, cleared samples originally weren't in our brain when we developed Lightsheet, because we thought this system is amazing for live cell, and cleared samples you can image on any microscope. But the more we thought about it, clearing really makes sense with Lightsheet. And it makes sense for a few reasons. The first is that cleared samples are big, and big samples, I mentioned earlier, large working distance tends to degrade your Z resolution. So in confocal, you don't get good Z resolution with big cleared samples. On Lightsheet, you do. The second is that cleared samples tend to be big, and therefore you want to go quick. And Lightsheet, because you image all of the pixels at the same time, it's quick. And then the third reason is some of these Lightsheet chemicals you don't want anywhere near your lenses, or you definitely want to be really careful with the liquid. And Lightsheet has really good liquid handling. So these 3 things came together, and we suddenly realized, okay, the Lightsheet does work well for clearing, and we adapted the product to be able to deal with that. So clearing will be covered more in the next talk, so I'm not going to go into massive detail, but basically you're trying to get your tissue to be more transparent, and there are a number of ways in which you can do that. Here on the left, you see brain before and after the clearing approach, and you see after the clearing approach, we can read the text underneath. Now, there are a bunch of different clearing methods, all of which have slightly different refractive indices. So in order to deal with that, we have a range of lenses and we have a range of chambers which are designed for these different refractive indices. And the short reason for why is, if you increase your refractive indices, you focus sooner, and therefore you need the cover slip to be a bit closer to the sample so that you can do that. So generally, yeah, as we go up in refractive indices, the cover slips move in slightly. And for the clearing setup, here we see a kind of typical example. This is a whole brain mount. We might do that at lower magnification or higher magnification. Here at lower mag, you see the size of this is about 13 by 13 by 6 millimeters. For some reason, it started to not play. I'm just going to restart my talk because the movies have got upset. Maybe. Okay. Yeah, here we see again, this is mouse trachea image with clearing both with a 5x and then with a 20x. And with cleared samples, the data can get quite big and quite quickly. This one is 725 gigabytes. It depends on how big an area, what the resolution is, whether you want to tile or not. The biggest data set, I think, taken on a Lightsheet is 42 terabytes, which was an entire brain at Nyquist, so you could see every part of every neuron. Now, again, I'm not going massively into clearing, but suffice to say, I'd mentioned there are different techniques. There is a handbook as well, which I think has been distributed. But really, clearing started with these organic techniques, the BAB, the BAP. And these, whilst they worked extremely well, they were quite hostile to the optics because they used benzene. And that not only was bad for the optics, it was also bad for some of the fluorophores. So GFP doesn't tend to withstand these techniques. And so at a similar time to when Lightsheet was becoming popular in 2005, 2006, there were people working on different clearing techniques which were much friendlier for fluorescence and were much easier to work with. They tend to be in these three main families. From Zeiss's perspective, we care about the refractive index and can we match to those. So that's why we have a series of lenses so that we can deal with a series of these wavelengths and clearing mechanisms. So yeah, I hope I've explained why the Lightsheet system is really good for anything big, whether it's live or whether it's cleared. This system just excels over other fluorescence microscopes. Yeah, it's a quick system. I'm not going to go through the rest of the list here, but just anything over 50 microns, 100 microns, the Lightsheet works really, really well for. I will mention, but it's not the focus of the talk today, people, of course, still work with cover slips. We do have one other system called Lattice Lightsheet, which is designed to look at cells on cover slips. So don't confuse the two. But yeah, as I mentioned, so that's the other system, the Lattice Lightsheet. We at Zeiss, we're selling both systems. And the main reason is Lattice Lightsheet is great for cell work, but anything over, when we get to spheroids, anything over about 50 microns, 100 microns, the Gaussian Lightsheet, so the main system I've spoken about today, becomes a better system for dealing with and handling with these large samples. 40 minutes, I'm on time. So what I will do, I'm open for Q&A and I will drop in. I don't use Zoom that often, so I'm trying to see how to drop my attachments in, if I can.
Thank you very much, Chris. please, if anyone has questions, you can write them either into the chat or you can go ahead and activate your microphone and ask. Maybe raise your hand.
See if I can put, aha. So I've just dropped into the chat 2 documents. The one which is marked ENWP clearing is about 11 pages, 12 pages, I think, and talks about clearing and some of the different techniques. The first one, the one that begins 000, sorry, I should have changed the file names, but this is a 44-page chapter from the manual which covers the different techniques. So if you're thinking, right, I've got fish, or I've got Drosophila, or I've got this, have a look through that chapter and it will give you an idea of some of the different ways to mount your samples. But if you've got something strange, yeah, feel free to ask now. Greg, you're muted, or I can't hear you. I see your mouth moving, but I can't hear you.
How about now? Is that working?
Yes, yes, ask away.
Okay, you had various holders here. So usually the holders, I presume, are somewhat expensive. So if you have a system, do you select 2 or 3 different holders separately, or how does that work?
Okay, there's 2 or 3 different things when it comes to holders. Let me try and find the overview here. Try and find the slide that matters. Or
Yeah, you had like
one or that. Right. First of all, in terms of this setup here, the main holder in the microscope is a metal stick. Is a metal stick like this. Okay. In that, you get, when you get the system, you get a bunch of glass capillaries and sponges and wires. That lets you do this technique really easily, the embedding technique. And those capillaries cost about 10 cents each, and the plungers you reuse. And the holder comes with 4 different sizes, so ranging from a few hundred microns up to about 2 or 3 millimeters. There's also a holder where you can get a 1 mil syringe and you can cut the end off. So the sample I showed with the big embryo kind of stuck in, you can do that. The hanging technique on the left, anything that you can hang off a capillary, you do that. So people just use the same kind of glass capillaries through this thing to do this technique here. The FEP technique on the right, what people tend to do is get FEP tube. Now, the FEP tube is cheap-ish. Yeah, if you buy a meter of it, it's really expensive. If you buy a kilometer of it, it costs maybe 3 times as much. So yeah, it's maybe 100 euros, 200 euros for a huge amount of FEP tube, and you cut a few centimeters and you tend to put that over the edge of the capillary. So really, the default holders will let you do these 3 techniques. When it comes to clearing, the clearing holders, we do sell some of these. So we have a few of the different brackets here, but the ones actually in the talk here are 3D printed. So we can provide the CAD design that lets you clip onto the end of the holder. And as long as you've got the right kind of connection at the end, if you have a 3D printer, it's whatever works. Usually with the clearing system, though, we tend to use a stub, which I don't think let me see. There was a slide I think I didn't show that shows the stub. Here we go. So this is the kind of mount here where you have a brain and you just use super glue to put it on the end of the stub. Okay, so it's a little bit that one of the ways I've heard the light sheet phrased is the good news is whatever you try, very often no one else has done it before, but the bad news is no one else has done it before. So we do a lot of very different mounting techniques here.
And but also the chambers that these fit into with the clearing. So the chambers are also, there are various different chambers.
Yes, so by default, you have a water chamber for refractive index 1.33. I must admit that I don't know which chambers you have on site here. So there's 2 or 3 different chambers for different refractive indices. So you just want to talk about, you want to check that your clearing technique is compatible with the chambers you have there.
We have the water and the clearing 20x.
Okay, the clearing 20x tends to be more based around 1.45, I think, typically. Okay, I see other hands up. So do you want to unmute and ask your question?
I don't know if Jose Antonio or Tobias, go ahead.
I think Tobias was first, so.
Okay, thanks, fair enough. Thanks, Chris, for a very interesting talk. I don't have any personal experience yet with Lightsheet, but I'm very interested to try it out. And I'm wondering, why do people always use round capillaries? So it strikes me that if you take a round sample and you turn it, you get a lot more resolution in the center of your sample, but it's not evenly distributed. So if you would take a square-shaped cuvette and you would move it laterally, you would get sort of more even sampling. Why is that not done normally, or what's the rationale behind that design?
Well, don't forget, you're not imaging through the, you don't image through the capillary. So when you image here, you have your glass capillary here, but you're not imaging through that. You're imaging through the aggro sausage, which is pushed out. And the aggro sausage, because it's made of aggros, you're trying to match it to the refractive index of the water. So your whole optical system is square, because you're going from, you know, chamber cover slips through water and then through, whether it's round or square, it kind of doesn't matter, because if the aggros is matched nicely, it doesn't matter. So people just use round capillaries and round plungers because that's what was available in the community. That's what's used in science. So we go with what's there. And to be honest, the plungers probably work easier round.
Thanks. Okay, that makes a lot of sense. Thanks. I hadn't really considered that.
No problem. I don't know who's next. So
I think it's me. Yeah, I work with avian bows with clearing methods, and one of the problems I found when using confocal microscopy is that bone is a really dense tissue, and usually, well, you have some level of problems with antibody penetration and another level of problem with laser penetration with thicker bones, usually having you have a harder time getting a clear image to the center of the bone. Is there a way to solve that with Lightsheet, or do you have some sort of
Lightsheet? Lightsheet won't make that necessarily easier. So one big question is kind of what goes deeper. In the early prototype days, we built a Lightsheet that had a Lightsheet, a confocal, and a multiphoton on system. And we did a lot of work looking at spheroids. Now, these are 600 micron spheroids. We got about 100 microns with confocal, 150. We got about 250 microns with the Lightsheet, and we got about 350, 400 microns with the multiphoton. I say we got about that. The thing you have to get your head around in Lightsheet is that in confocal, when you go deep, when light scatters, your image goes black. In Lightsheet, your image goes fuzzy. So you have to think, what do you care about? If you care about resolving to actin filaments, a confocal will go deeper than Lightsheet. If you care about counting nuclei, which are big blobs, then Lightsheet will go deeper. But in terms of the magical recipe for depth penetration, it's still a light-based system. So that's where clearing, yeah, you need to clear. And also probably the thing with things like bone is you need to think about the angle you're coming in at, because you need to get the light in at the side and out from the orientation you're looking at. So yeah, I won't pretend that Lightsheet is going to be easier for you. If you can clear it somehow, then at least, yeah, if it's cleared, at least it'll be able to image it quickly and with good Z resolution. But yeah, bone's not an easy thing.
Yeah, well, thank you. Thank you.
Juan Rodriguez, do you want to, you're muted. Do you want to ask?
Now, can you hear me now?
Yes.
Yeah, nice. And I mean, thanks for the talk. Nice images. And I have like 2 questions. First, like how easy is to change the your acquisition objective? Like, do you need to remove the sample, to remove the buffer from the sample chamber? And second, you have a 2-side illumination light sheet, right? With one acquisition arm. How do you deal in the multi-view fusion, like when you have, like, for example, samples that are not homogeneous, so then you have probably like scattered light not in the same range between the 2 illuminations, so one side could be a bit more defocused. So is that done automatically with the software, or you have to check that manually to set the parameters?
Okay, good questions. In terms of changing the chamber and the lenses, do I have a picture here? Usually it depends on the chamber you have, and it depends on the sample you have. Usually changing the chamber, you at least need to move the sample up and out of the way, or in the cleared one, it can rest on the chamber. You would then open the door, unscrew the chamber, pull it out, and then you change the 3 lenses. For someone trained who knows what they're doing, it's about 5 minutes to change between a water set and a clearing set. So it's not instant, but 5 minutes, 10 minutes if you don't know what you're doing. So yeah, usually on a system we would say, yeah, do your water samples on a Monday and Tuesday and your cleared samples on a Wednesday and Thursday. So you're not changing all the time, but it's not that bad. The other thing is that one of the reasons for changing the chamber and the lens on a normal microscope is to adapt the field of view. And I don't think I mentioned it specifically. On the light path here, there's a really good zoom lens, which goes from 0.3 to 2.5. So what that means is, in normal terms, if you're imaging with a 20x lens, without changing the chamber or the lens, you can change that lens to be a 7x or a 50x and anywhere in between. So it's really, you can zoom out, get the overview, that's where I want to go, and you can come on in. So that's the lenses in the chamber. On the second question, you talk about, okay, if this is the imaging lens coming from above, you're saying the 2 sheets here, potentially one's like that and one, yeah, they might not be in the same plane here. Each of these you adjust. So you have an adjustment, it's a slider in the software, and you adjust one side and you adjust the other side. And the way you usually do that is you basically make them the sharpest. So if they're out of focus, they're blurry. So you would adjust, and you go blurry, sharp, blurry, and you would do that for each of the 2 sides so that you know that they're in the same plane. If you have a really, really thick sample, then you might want to take, the first millimeter, and then you might want to adjust the sheet and take the next millimeter. But yeah, most of the time it's just you adjust the 2 sides.
Okay. And just related to this this optional zoom that you have, like between this 0.3 and 2.5.
Yeah.
Is any change in terms of the resolution? I mean, like axial resolution.
Yes. So what happened? Yeah, what tends to happen is because you have a Gaussian sheet. So if you imagine my zoom camera, you've got your 2 sheets coming in here. Your Gaussian sheet is thinner in the middle than it is at the edge.
Yeah.
Now, the first time we did a Lightsheet conference back in 2009, 2008, all the home builders asked each other, they said, how do you choose? Do you make it because if you make it thicker in the middle, you can be more uniform. Or if you make it really thin in the middle, it's massive at the outside. And everybody had independently come up with this way of saying, we set it twice as thick at the edge as in the middle. And the reason they do that is because the axial resolution is determined by the excitation and the emission PSF, you tend to not notice any difference. You get a reasonably uniform Z section across the range. On the light sheet, as you zoom in, so as you go from a 50x field of view to a 7x field of view, that adjustment is automatically done. So it automatically adjusts. So as you zoom into a 50x, your Z resolution does get slightly better, but it will tell you that in the software.
Okay. Thanks.
Okay. Okay. What I suggest, because of time, if we move on to the next talk, I'll hang around. So if you've got other questions, you can ask them in the chat, or I'll put my email in the chat as well. So if anything pops up later.
Chris, can I just ask you quickly to jump to slide 39?
Yes.
I have a question on the enclosed. So is that not in a tube? Because you were saying that you're not looking through a glass tube, like Tobias had this question. And so in this tubing that you have this, is that not?
Yes. So in the middle method, the embedding method, you have a glass capillary and you don't image through the glass because it will look terrible. It just refracts the light. In the encapsulation method, the trick is to make a chamber which has the same refractive index as water, so the chamber becomes invisible. So in the early days, before we commercialized systems, the EMBL used to make a bucket out of agros. So imagine a jelly mold. So you make a mold, pour agros in, put a hole, and that's how they contain things. And then by accident, they discovered that FEP, this plastic used in flow cytometry tubes, has a refractive index so close to water that you can image through it.
Okay.
It's a lucky coincidence. It's not quite. If you were to look at a method on the left versus a method on the right, there's a slight drop in resolution, but for all the benefits it gives you. So as a benefit, for example, we were trying to do mouse embryos. The mouse embryos are tough. If you put them in agros, in the 5 minutes it takes you to put them in the microscope, they are dead. Doing the right-hand method, we got them to live for a few hours. By doing the right-hand method and preheating the tube and doing everything under exactly the right CO2 controls, we can now image early-stage mammalian embryos for 48 hours. So this is really your super friendly technique on the right.
Okay, thanks.
Okay, right. I'll go on mute and jump in the chat and hand over for the next clearing talk.
Thank you so much, Chris. And so,
Stop.
okay, Ramon can maybe start sharing his screen to talk about clarity and his experience and his nice clarity apparatus that he built.
¿Me escuchan?
Yes.
Sí. Ya, perfecto. Bueno, yo les voy a hablar un poco de la técnica de Clarity y la experiencia que hemos tenido con ella. Desde que nos ganamos el microscopio comenzamos con esta técnica, ya que sabemos que es imprescindible para poder visualizar muestras en el microscopio Lightsheet. ¿Ya? Voy a hacer, la charla se llama Una mirada a través del tiempo en la técnica de clarificado, y quiero que podamos compartir al final con la gente que haya hecho esta técnica algunos tips para poder ir avanzando con esto, ¿ya? Primero, comenzar con algo que es básico, pero es importante que todos tengamos claro, ¿Para qué realizamos el clarificado de las muestras? ¿Cuál es la necesidad de hacer esto? ¿No es cierto? Entonces nosotros podemos decir que cuando un material contiene una mezcla de componentes de pequeño tamaño con diferentes índices de refracción, las interacciones de la luz con estos componentes heterogéneos conducen a una falta de transparencia, ¿ya? Entonces, ¿qué buscamos con esto? Homogeneizar el índice de refracción de la muestra, quitando, reemplazando y modificando algunos de sus componentes, ¿ya? Para poder visualizar, ¿no es cierto?, muestra en el microscopio, necesitamos, ¿no es cierto?, que la luz entre lo más pareja posible y podamos visualizar dentro de nuestra muestra que son tejidos grandes, ¿ya? La finalidad en lo que nosotros vamos a ocupar esta técnica en ciencia, principalmente, ¿no es cierto?, como decía, es para volver la muestra transparente, ¿ya? Y también evitar, de alguna forma, realizar cortes seccionados, ya para lograr esta estructura tridimensional, ya que el realizar este tipo de trabajo puede llevar a muchos errores, y por la distorsión mecánica de los tejidos causados por los cortes histológicos, ¿no es cierto? Y la reconstrucción 3D lleva mucho trabajo también y es imprecisa, ¿ya? Entonces la necesidad de poder obtener una muestra completa surge, y ya tenemos las tecnologías para poder realizar este tipo de técnicas, ¿ya? Entonces, en base a esta necesidad, se generaron un sinnúmero de técnicas que tienen diferentes características y ventajas y desventajas, ¿ya? Las cuales vamos a ir nombrando una a una, y vamos a ver por qué elegimos la técnica que ocupamos actualmente. Principalmente, existen muchas técnicas de Clarity, pero las podemos dividir en tres formatos, ¿ya? La hidrofóbica, la hidrofílica y la de hidrogel. Como les comentaba, cada una con sus ventajas y desventajas que vamos a ir viendo a continuación. La primera la podemos llamar como la que se utilizan disolventes orgánicos. Son métodos que deshidratan la muestra, ¿ya? Extrayendo los lípidos y homogenizan el índice de refracción a un valor alto, alrededor de 1,55. Las ventajas de esta técnica es que son extremadamente rápidas, ¿ya? Pero las desventajas es que son la penetración de los anticuerpos de las muestras grandes demora mucho. También esta deshidratación hace que las muestras disminuyan su tamaño, ¿ya? Y una de las principales desventajas que tiene son que utilizamos sustancias tóxicas que pueden dañar tanto la fluorescencia de la muestra, ¿ya?, como también los objetivos. Por tanto, se necesitan requerimientos especiales de los microscopios para poder visualizar este tipo de muestras. También tiene problemas con la mantención y la preservación de la fluorescencia, y como les comentaba, existe una contracción de la muestra debido a la deshidratación. Otra de las técnicas que existen, ¿no es cierto?, son en soluciones acuosas de alto índice de refracción. Estos métodos sumergen la muestra en soluciones acuosas que tienen un índice de refracción en el rango de 1,4 a 1,52, buscando conseguir el índice de refracción. Las ventajas son la simplicidad de la técnica y la conservación de los lípidos, pero la principal desventaja es que esta forma de limpieza es bastante clara, o sea, bastante cara, son extremadamente caras, ¿ya? Y son lentas también. Como tercera son las soluciones hiperhidratantes, ya, y el mecanismo propuesto para este tipo de técnicas es la eliminación de lípidos con detergentes, altas concentraciones de urea y una solución final con un índice de refracción en el rango de 1,38 y 1,48. Los métodos más conocidos son el cubic y el scale. Las ventajas son su simplicidad, una buena limpieza, rendimiento y que mantienen las proteínas fluorescentes. La desventaja es que la limpieza puede tomar varias semanas para muestras grandes. Por lo tanto, si el método es compatible con la inmunización, posteriormente, ¿no es cierto?, la combinación de largos tiempos de limpieza es su limitante, ¿ya? Agregado que cuando uno hace la inmuno luego, también requiere de bastante tiempo. La cuarta técnica es la del hidrogel, que es la que tiene mejores comentarios y es la que nosotros hemos desarrollado en el laboratorio. ¿Ya? Y estos métodos estabilizan las proteínas de la muestra mediante la reticulación de ellas en un hidrogel. ¿Ya? Se extraen los líquidos con detergente y luego se sumergen en una solución con un índice de refracción de entre 1,38 y 1,45. Estas soluciones pueden ser muy variadas y de bajo o de alto costo, dependiendo de la técnica que se utilice. También se divide este tipo de técnica en un sinnúmero de opciones, ¿ya? La ventaja principal es que de estos métodos son excelentes para limpiar, ¿ya? Mantienen la fluorescencia de las proteínas y tiene un alto rendimiento. La desventaja principal es que es difícil de implementar de alguna forma porque requería de equipamiento bastante caro. Requiere electroforesis, perfusión constante, lo que quiere decir que se tiene que estar limpiando constantemente este líquido de limpieza y se ocupan en altas cantidades. Además, las soluciones de coincidencia del índice de refracción también son bastante caras, pero ahí vamos a ver algunas opciones que han funcionado bastante bien para disminuir los costos y para poder ir realizando esta técnica ya funcional dentro de un laboratorio. Bueno, como les comentaba, el fundador de esta familia de métodos se llama Clarity, ¿ya? Que ha sido modificado por diferentes laboratorios para ir mejorando su rendimiento, como les comentaba. Entre estos métodos más conocidos está el PAC, el ACT y el switch, ¿ya? Y ahí los vamos a ir comentando a continuación. Estos métodos han tenido grandes resultados, tanto para mapear la actividad cerebral y proyecciones neuronales y la visualización de algunas bacterias, ¿no es cierto?, en infecciones profundas en pulmones. Incluso esta técnica se ha utilizado para limpiar huesos. Principalmente, estas últimas tres técnicas que yo les comentaba, consiste en fijar la muestra, ponerla en este hidrogel, ¿ya? El cual se activa se le aplica un activador, y luego se aplica como tercer paso la electroforesis, si es que es el método Clarity o el activo, o el método Clarity, o sea, de clarificado activo, ¿ya? O se puede dejar en el detergente a alta concentración durante mucho tiempo, ¿ya? Que sería el método pasivo, que es el PACT. ¿Ya? Los tres tienen buenos resultados, pero el Clarity, que requiere electroforesis, tiene bastantes problemas en el sentido de que necesita un equipamiento especial, y los electrodos también son bastante caros como para hacerlo en un laboratorio, ¿ya? Pero hemos desarrollado algunos métodos que han abaratado los costos de esto y ha funcionado bien, y los vamos a ver a continuación. Bueno, como les comentaba, está el Clarity, ¿no es cierto?, que ha ido derivando al clarificado activo y al pasivo, que también han ido derivando en muchas más técnicas. en base a lo mismo. Incluso van mezclando estas técnicas para lograr mejores resultados. El Clarity pasivo, como les comentaba, es dejarlo en una solución de detergente durante mucho tiempo principalmente. El tejido en el hidrogel se deja durante mucho tiempo. Y está el Clarity, o sea, ese es el Clarity pasivo. Y el Clarity activo se pone la muestra que está en el hidrogel, ¿no es cierto?, en una electroforesis constante. Esto disminuye los tiempos para realizar el clarificado, pero tiene algunas contraindicaciones como que genera muchas burbujas, los electrodos tienen que ser de platino, y es bastante caro realizar este tipo de técnica. Ya también requiere que esté constantemente un flujo del buffer de lavado, ¿no es cierto? O sea, de lo que ocupamos para ir clarificando, que es el SDS, y también tiene que ir siendo filtrado continuamente. Ya para esto se diseñó, hay una máquina, o sea, un equipo que es bastante caro también, que está hecho exclusivamente para realizar este tipo de técnica, y también existe una gran cantidad de publicaciones donde cada laboratorio ha desarrollado su propio sistema de electroforesis y de sistema de flujo continuo. ¿Ya? Nosotros en nuestro laboratorio hemos hecho ambas técnicas, donde principalmente para el método pasivo lo dejamos en un matraz, ya en un Falcon con orificios, ya, y esto está en un sistema que vaya girando, ¿no es cierto?, para ir renovando el buffer de clarificado. Y esto requiere temperatura, y uno tiene que estar constantemente monitoreando tanto el pH como la temperatura, y ir filtrando este método este buffer de lavado, ¿no es cierto? Hay que estarlo constantemente filtrando. ¿Ya? Esto es para muestras grandes, y para muestras más pequeñas las ponemos en un sistema de pipetas Pasteur, donde ponemos dentro la muestra, que si son, por ejemplo, un nervio ciático, o cosas más pequeñas, ¿no es cierto? O sea, tejidos más pequeños, y con el mismo sistema de recirculación. ¿Ya? Y lo más importante es siempre ir monitoreando la temperatura y el pH. También diseñamos un sistema de electroforesis que funcionó bastante bien, y cambiamos los electrodos de platino por unos electrodos de carbono, ¿ya? Que no generan calor, que era uno de los problemas de los electrodos también de platino, que generaban demasiado calor y quemaban la muestra. Y funcionó súper bien, acortando los tiempos en comparación con el Clarity pasivo. ¿Ya? Principalmente para probar esta muestra corrimos un gel y dejamos durante 14 horas los cerebros en este sistema de electroforesis, que va en otro sistema, que es este sistema de recirculación, donde acá está la electroforesis, o sea, está ocurriendo la electroforesis, y va el buffer circulando a través de estas mangueras, y es filtrado, se filtra, ¿no es cierto?, y vuelve nuevamente al sistema de electroforesis. También la temperatura está siempre controlada, y esto acortó bastante los tiempos de clarificado del cerebro. De todas maneras, yo hice una combinación y un preclarificado con el método pasivo, y luego aplicamos este método de electroforesis, que duró aproximadamente 7 días, en comparación con el método pasivo, que duró 3 semanas. A través de estos dos métodos hemos hecho diferentes tejidos, incluyendo cerebros en cortes de 2 a 3 milímetros, cerebros de mosca incluso hemos intentado hacer, cerebros completos, que el único detalle que podría comentar es que quedan un poco de un color amarillo, ¿ya? En el caso del cerebro, con esta técnica, no sé si alguien tiene alguna experiencia con esto, pero quedan un poco amarillos, pero sí transparentes. En el caso de intestino, funciona súper bien y los deja completamente transparentes, al igual que con los nervios, nervio ciático y nervio óptico, que también hemos hecho esta técnica. En el caso del cerebro, hemos logrado visualizar sin problema, al menos de la técnica clarificada. Ahí les voy a comentar luego otros problemas que hemos tenido, que es lo que de la pregunta que hicieron en la charla anterior, que es la penetrabilidad que tienen los anticuerpos o las tinciones luego de realizar esta técnica, ¿ya? Con otro grupo de investigación que también están desarrollando Clarity, hemos ido complementando y encontrando algunas soluciones respecto a estos inconvenientes que se han tenido al desarrollar esta técnica. ¿Ya? Bueno, estas son algunas fotografías que hemos tomado, en este caso con el anticuerpo de la beta-3 tubulina en cerebro, en donde no, también en nervio ciático, ¿ya? Hemos obtenido buenos resultados en el sentido de que ha penetrado bastante el anticuerpo, a pesar de que tuvimos al principio muchos problemas con diferentes técnicas de Clarity, e incluso con esta también, pero ya hemos logrado con algunas soluciones que le voy a dar después, de obtener bastante penetrabilidad de los anticuerpos que hemos utilizado. Donde no existe problema es en el intestino. El clarificado es extremadamente rápido, queda muy transparente y la penetrabilidad del anticuerpo no tiene mayores problemas, ¿ya? También hemos hecho esta técnica en piel, donde han tenido buenos resultados también, porque no existe tanto problema en los tiempos de clarificado, y además el anticuerpo penetra bastante bien en la piel. Esto es nervio óptico. Alguna fotografía de nervio óptico que hemos tomado, esto es en confocal. Sin mayores, o sea, ahora utilizamos un protocolo para que logre penetrar bien el anticuerpo, utilizando enzimas para poder ayudar a que el anticuerpo se incorpore mejor. Estas son fotografías de otro equipo de investigación que vino a nuestro microscopio, al Lightsheet, y obtuvo este tipo esta fotografía, ¿ya? Y ellos también nos dimos cuenta que también tenían el mismo problema que nosotros de la penetrabilidad de los anticuerpos. Y ahí estamos comentando qué es lo que podemos hacer, y ojalá que después de esta charla, si alguien tiene experiencia en este tipo, mayor experiencia en este tipo de técnicas, podamos comentar qué es lo que se puede hacer para lograr tener mayor penetrabilidad del anticuerpo, como les comentaba. Bueno, desafíos de la técnica a tener en cuenta o en consideración, ¿no es cierto? Que se ha sugerido que lo que es crítico de la técnica para lograr un buen clarificado es mantener súper estable tanto la temperatura como en los cambios de pH. Y el bloqueo de la corriente, ¿no es cierto? Que no exista bloqueo de la corriente por las burbujas que se realicen. Esto último es fácil de solucionar con el sistema de recirculación, ¿no es cierto? Que tiene que estar siempre funcionando. También es importante que cuando uno haga esta técnica, para lograr que sea homogéneo, la extracción de los lípidos, siempre ir cambiando la polaridad cada 3 horas, cambiando la polaridad de la electroforesis. O si no, la muestra se puede desarmar un poco con este tipo de técnica. ¿Ya? Y normalmente cuando hay cambios de pH que me ha sucedido, la muestra queda amarilla y no se logra transparentar de ninguna forma. Bueno, el problema que les comentaba, ¿no es cierto? En esta imagen podemos ver, ¿no es cierto? En esta imagen axial, que por dentro, o sea, era el problema que teníamos al principio, de que por dentro de la muestra, ¿no es cierto? El anticuerpo no penetraba bien. ¿Ya? Eso se podía ver cuando sacábamos la fotografía y veíamos que al interior el anticuerpo se quedaba solo en la superficie, ¿ya? Y no lograba penetrar bien en la muestra. Bueno, en respuesta a todos estos problemas que tuvimos en respuesta a estos problemas que tuvimos, ¿no es cierto?, encontré un paper que se llamaba, una técnica que se llama ACT Presto, ¿no es cierto?, que es la técnica de claridad activa relacionada con la presión, eficiente y con la presión eficiente, ya que lo que hace es realizar la inmuno a través de una centrifugación a 600 G durante 12 horas o 6 horas aproximadamente, y separaba la centrifugación y había que hacer recambio o sea, había que ir moviendo la muestra. Y esto resulta súper bien para que el anticuerpo no se quede pegado por el borde o sea, por la superficie de la muestra, y se logra mucho mayor penetración de los diferentes anticuerpos que estemos utilizando. También tratamiento enzimático antes de hacer la inmuno. También he visto algunos papers que yo no lo he probado, de también intentar hacer una electroforesis, ¿ya? Utilización de nanoanticuerpos, que tampoco lo he probado, pero varios papers dicen que aumenta, o sea, uno puede acortar mucho los tiempos del inmuno y que tienen alta penetrabilidad, y también ocupar anticuerpos más pequeños como el FAB2. ¿Ya? Eso sí lo hemos utilizado y sí acorta mucho los tiempos, y la penetración del anticuerpo es bastante buena. Esa sería la presentación. Ahora, es importante mencionar que el día 15 nosotros vamos a hacer un curso donde esperamos que todos puedan traer sus muestras. Voy a enviar una encuesta para saber qué tipo de muestras quieren clarificar a las personas que se inscriban en este pequeño curso que vamos a hacer, para que vayamos viendo cómo lo vamos a ir organizando y saber también qué tipo de muestras van a llegar, ¿ya? Para poder, porque depende del tamaño y del tipo de muestra, los tiempos que vamos a utilizar durante este curso.
Thank you, Ramon. If anyone has any questions, please write them in the chat window or activate your microphone to ask. I know we already have like 21 participants that are interested to take this course on June 15th. And if everybody will be bringing a sample, we might have to stagger how we use the Clarity equipment. So probably 5 or so people can process their samples at a time, and it takes about a week. So we'll have to sort of stagger how we do it. But please do sign up so we can check your samples out.
I guess the beauty is if you can't get them in the first go, at least they're not going to die.
Yeah. Okay, I don't know if there's no questions. I mean, you can go ahead and ask them in Spanish. I'm sorry, I'm not speaking Spanish, but it's okay to ask in Spanish. But let me see the chat box. Okay, how can you apply to this course? Okay, I sent a Google form. Let me see if I can find the link to it. It's on the email, but if you didn't get the email, I can try to find it now. Let me see. Okay.
Alenka, ¿podría dar mi mail en el chat? No puedo.
Okay, you can, I mean, that's true. You can write to Ramon or you can sign up on the form that I've pasted into the chat window.
Bueno, a los que estén interesados, que estén acá, espero me puedan mandar un mail para que yo los contacte con esta encuesta que vamos a hacer para saber qué tipo de muestras, si es que quieren. Lo ideal sería que cada uno trajera su propia, la muestra que quiere clarificar y ojalá si tienen los anticuerpos también para poder realizar la técnica y la podamos ver en el Lightsheet. Y organizar los tiempos, sobre todo eso.
All right, so if there are no more questions, I want to thank both of our speakers. Thank you so much, Chris, for your presentation, and thank you, Ramon. It was wonderful, and let's continue with this topic of clarity, and let's use the machine.
A pleasure. Thank you.
All right. Thank you very much.
Gracias.
Bye-bye.